Hi everyone, and welcome back to part 2 of this video series on semiconductors. So today we'll be talking about the energy bands of a semiconductor. So first, what is a semiconductor even? So semiconductors are devices with a conductivity that's between conductors, like for example copper, which is a metal. So these have very good conductivity, and also insulators like glass or plastic or something like that. And then a unique thing about semiconductors is their conductivity can actually be varied largely by changes in temperature, optical excitation, and their electrical properties can be changed by a process called doping, which is basically adding impurities inside the semiconductor crystal. We'll look at doping, which is very, very important and forms the foundation of every single device we have now in a future video. So another thing about semiconductors is they have a bandgap energy of below 3 eV, which is electron volt. It's another unit for energy. So 1 eV is just equal to 1.6 times 10 to power of negative 19 joule. So what is bandgap energy actually? We'll take a look at it later in this video, but essentially it is the energy difference between the conduction band, which contains electrons that are able to be responsible for electrical conduction, so they can participate in they can participate in charge movement, for example, to conduct electricity, and also the valence band, which is the highest occupied energy by electrons at absolute zero temperature. So in between the conduction and valence band, which is something like that. So EC is the minimum of the conduction band, and EV is the top of the valence band. There's a middle, which is the forbidden band or forbidden energy level or band gap, which no electrons are allowed to exist here. So if they want, they can go directly to the conduction band or directly to the valence band and not in the middle. So first, what are electrons and holes? So as we know, electrons is just a particle with a charge of negative 1.6 times 10 to the power of negative 19 coulomb. And then, so hole is basically just the absence of an electron. So holes also have a charge, and then since that is an absence of electron, the charge is positive 1.6 times 10 to the power of negative 19 coulomb. Alright, so let's take a look at how this band diagram is formed in the first place. So first, we'll look at bonding of hydrogen. So we know that the electronic configuration of hydrogen is 1s1 because it only has one valence electron. So let's look at what happens when two hydrogen atoms come close to each other. So before the interaction, each of these hydrogen atoms have one electron in the 1s state or 1s wave function. So you can see this and this. And then once they come closer to each other, because of the Pauli exclusion principle, which states that in a given electron system, there are no two electrons that may have the same quantum state. When they approach each other, what the 1s waves functions will interact to form, this is called an interaction, to form wave function A and B, which is here and here. And then these wave functions A and B contain energy of EA and EB respectively. So this formation of the bonding and anti-bonding, so this is the bonding energy and this is so-called the anti-bonding energy. And then you can see the delta E is the bonding energy here. So the formation of this EA and EB is called energy splitting. So yeah, that's how two hydrogen atoms sort of interact once they approach each other. So now let's look at silicon, which is the most common material used to make semiconductor, and its electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p2. So this, I'm not going to explain how this is obtained. You should have done it in any high school chemistry syllabus. And so I'm going to explain how this energy diagram or band diagram is obtained. So as the interatomic distance decreases from infinity, which is, so we are looking at from right to left, we'll first take a look at the 3s2 band. So this 3s2 band, as you know, that the s orbital can contain two states. So if we have n amount, there's 2n states in this s band. And then the p band has 6 states. So you should have also learned this in chemistry. So the p band has 6 states and S has 2 states. So there's obviously 6 n states in the p band. And so for silicon, there's only 2 n electrons in the p band, but there's 2 n electrons in the s band. So as the 2 n states of 3s interact, they form a 3s band. So the energy levels split, as you can see. So this is sort of the 3s band, as I've circled in green. And because there are only 2 n states and there are 2 n electrons, all states are filled. And so this is the similar case for the 3p6 or 3p, yes, like 3p band. So there are 6 n states and 2 n electrons, so there are 4 states empty. And then energy levels also split and causes this 3p band. So all the states in 3s2 are filled, but only 2 n states in 3p2 or 3p6, so p band anyways, are filled. So now we are actually here. And then once the interatomic spacing decreases further, I'm just going to erase everything here for now. Once the interatomic spacing decreases further, you can see that these two bands meet. So they merge, and then they form a single, the word is called merge, and then they form a single 3s 3p band. So as you can see, there are 6 n states on the top and 2 n states at the bottom. So when they merge, they form 8 n states. And then there is still only 4 n electrons. So obviously there is 4 empty states. So as you can see in this place we are looking at here now, there are 8 n states and 4 n electrons. Okay, so let's erase this now. And then we'll continue to make the interatomic distance even smaller. So now that the interatomic spacing decreases, so we are here now, and as the interatomic spacing decreases towards the equilibrium interatomic distance, or R or A, depending on what your graph or question uses, the 3s and 3p or the 3s 3p band splits again. So they split like this. So the top is the p band and the bottom is the s band. So they split into 2 bands and they are separated by a band gap. So this is the band gap we were talking about earlier. So they are separated by a band gap or band gap energy, which we will put as Eg. So the band gap energy is Eg. So at 0 Kelvin, which is absolute 0, all electrons will take the lowest energy state they can. So in this case, because there are 8 n states and 4 n electrons, they will still take, all the 4 n electrons will take the valence band. So because all the electrons will take the lowest energy possible at absolute 0, all 4 electrons will take the 4 n states in the valence band. And the conduction band is fully empty with 4 n states and 0 electrons. So that is how it's formed. So now we have a question. What happens to the band gap of a semiconductor when the temperature of the semiconductor increases? So let's examine this. As the temperature of the semiconductor increases, there is more vibrations in the lattice, so the equilibrium interatomic distance also increases. So now, instead of here, maybe the equilibrium interatomic distance is now here at the dotted line, and the new band gap is here. So as you can see, the band gap decreases. So as for most semiconductors, as the temperature increases, the band gap decreases. So yeah. So as we have said earlier, we can draw this band diagram like this, where EC is the bottom of the conduction band and EV is the top of the valence band, and they are separated by a band gap. So here is the conduction band and here's the valence band. But with an electric field, it changes things a bit. So with an electric field, now the energy band diagram looks like this, and the energy band diagram is actually inclined at a gradient proportional to the electric field. So the electric field is towards here. So yeah, as you can see, the energy band is now inclined at a gradient. So the equation for this is 1 over Q, where Q is the elementary charge, which is 1.69 no, 1.6 times 10 to the power of negative 19. So Q is this. So this equation is actually provided in the formula sheet, but basically you can see the band gap is still the same. So when there's an electric field applied, the conduction band and the valence band, or like the entire band, will be inclined at a gradient proportional to the electric field. Alright, so now let's look at the excitation of electrons. So first, what does excitation actually mean? Excitation is when an electron is elevated or transferred to the conduction band from the valence band. So for example, at absolute zero, there's many electrons in the valence band here. Remember, because all the electrons occupy the lowest energy state. And now when the temperature is increased slightly, okay, so there are two ways to excite electrons to the conduction band. One is through temperature and one is through optical illumination, which is also light. So we'll first look at temperature. So for example, if now one of the electrons gain enough thermal energy, where the thermal energy is larger or equals to the band gap energy, so it'll form a hole here and it'll be excited to the conduction band. So again, remember that nothing can exist in the forbidden band, so it cannot be like excited halfway. It has to be excited fully to the conduction band at one time. So, and this will happen when the thermal energy is larger than the band gap energy. So as the temperature increases above 0 Kelvin, more and more electrons will have enough energy to jump to or be excited to the conduction band. So the semiconductor gets more and more conductive as the temperature increases. So of course, when one of the electrons go to the conduction band, we can see that it leaves behind a hole here in the valence band. So this is called an electron-hole pair, because the electrons and holes are created in pairs. So the number of electrons in valence band is also equals to the number of electrons in the conduction band. This is for an undoped semiconductor. For doped, we'll take a look at that later. But yeah. And then another way is through optical illumination. So the electrons in valence band are excited through photon energy, which we'll call EPH here. So for it to work, again, it's the same thing. The EPH must be larger than the band gap energy so that it can be excited directly instead of in the middle. And the photon energy is equals to this, which is provided in your formula sheet. So H is the Planck constant, C is the speed of light, and then the lambda is your wavelength. So this is all in SI unit. Or you can write it like this because it's larger than the band gap energy. So normally we'll take a look at EG in terms of electron volt, and we'll look at wavelength in terms of nanometer. So another way to write this is very close approximation is 1242.37 divided by this, and this is in nanometer, is larger than the EG, which is in electron volt. So this number is quite convenient when you are solving questions. Now let's look at the movement in a semiconductor, so how the carriers move. Remember just now we were talking about how a hole is just the absence of an electron. So how do holes actually move? So let's imagine this. You see we have 3 silicon lattice here, or rather we have 1 silicon lattice, and then each of this is the next time interval. So this is original and this is the first time interval right after this, and then this is right after this. So let's first draw a hole here. So obviously to form a hole here, an electron from this bond moves somewhere else. And then let's just say that a blue, just gonna put here in blue, this blue electron here moves to fill this hole. So now in the next instant after this, obviously we have this blue electron already here, and then let's say now we have a hole here because the electron has already moved to this. So okay, so this is the same as this. So now there's a green hole from here, and then to fill this green hole, let's say another electron here, a green electron, moving to this hole. So now again in the next instant, how does it look like? It looks like this. So we have a green electron here, we have a hole here. I'm just gonna color this hole red. and then obviously this point here just now was blue. So now we have a blue electron which was originally here, and a green electron which was originally here at the red hole. So and then we have another red electron going to fill this hole. So as you can see from each of the time intervals, although it is the electrons that are actually moving, this hole is effectively also moving. So that's how you can imagine how the holes move through the movement of the electrons. So yeah, that's how carriers move in semiconductor. And we look at an example here, it should be quite easy. Gallium arsenide has a bandgap energy of 1.42 eV at 300K. What's the maximum wavelength of light to create electron hole pairs? So okay, first, what is an electron hole pair? As you can recall, when the electrons are elevated or excited to the conduction band, oh sorry, wrong way around. There's a hole here and an electron here. So as you can see, when they're excited to the conduction band, it leaves a hole and it brings the electron. So this is called an electron hole pair because the electrons and holes are created in pairs. So this is for an undoped semiconductor. For doping, we'll look at it in a future video. But so basically, because the number of holes in the conduction band is equal to the number of holes in the valence band for an undoped semiconductor, we can call it an electron hole pair. So for this, the photon energy again must be larger than the bandgap. So okay, larger or equals to the bandgap energy, and then so we can find the maximum wavelength here, which is approximately 875 nanometers. So that's the answer, 875 nanometers. Alright, so let's look at the direct band-to-band generation and recombination now. So just now, what we were talking about is how electrons are excited to the conduction band. So this is so-called EHP, so electron hole pair, remember? Electron hole pair generation was what we were talking about just now. But obviously, we can't just keep having generation without recombination, right? Else just bringing the semiconductor from 0 Kelvin or just bring it to like negative 250 degrees Celsius will just make it super conductive because all the electrons will just keep moving to the conduction band. So obviously they will also need to recombine. So recombination is when the electron drops from the conduction band back to the valence band. So this is called recombination. So it's the opposite of EHP generation, so EHP recombination. So they will also recombine. And then at a steady state is where the generation rate G, which is, remember just now we were talking about two ways, so temperature and also through optical excitation. So the generation rate is equals to both the temperature plus optical excitation generation. At steady state, this is equals to the recombination rate, which is expressed as R. And then at thermal equilibrium, the semiconductor at a certain temperature will have no external excitation, so it will have no optical excitation or other forms of external excitation, and it will only be excited through thermal excitation. So this is what they mean by when a semiconductor is at thermal equilibrium, or the thermal equilibrium electron and hole concentration. So yeah, again, thermal equilibrium electron and hole concentration is N0 and P0 respectively. So why it's called N0 and P0, you'll understand it in a future video, but it's because an N-type semiconductor is doped with excess electrons, and a P-type is opposite, so P-type is with excess holes. So that's why they are termed like N0 and P0, but basically these are the thermal equilibrium electron and hole concentrations. So now let's look at the EK diagram of semiconductors. So this is not really tested very often, but it's important to understand. So the EK diagram of a semiconductor is what you see here. So this is the energy to K. So K is the wave factor. So what does this actually mean? So you know, in classical physics, we have the kinetic energy is equals to half mv square. So you know, this is in classical physics. EK, so kinetic energy, is equals to this, is equals to p square over 2m. So for quantum physics is slightly different. So we'll first look at the crystal momentum in the x direction. So the crystal momentum in the x direction, which is this is a crystal momentum. So I'm not covering anything in the appendix or not tested here, but the crystal momentum is equals to the h bar, which is the reduced Planck constant. Oops. So this h bar is actually equals to Planck constant divided by 2 pi. So it's equals to the h bar divided by the wave vector on x direction. And so similarly, the EK is equals to, so you can see it's sort of px squared. I mean, if you think about the classical way, so it's equal to px squared over 2m, which is h bar squared kx squared over 2m. So as you can see, this is sort of a parabola. It will look something like a parabola. So parabola, because it's a hk all squared. So, and then from the EK diagram here, this is the reduced K space. So if we look at the reduced K space, so reduced K space means we only look at like one interval here instead of all of them. So for example, the reduced K space here in the conduction band, you can see it's here. And then this curve is actually really complex. So we take a parabolic approximation here at the lowest point of the conduction band. So similar to the valence band, we take a parabolic approximation here. So with this parabolic approximation, we can get this. We can get this. So that's how this is obtained. This is obtained through a parabolic approximation. All right. So that's how it works. And there's one more equation that you need to take note of. So you are not required to derive this in the exam, but this is the equation. So it's also provided in the formula sheet. So 1 over n star. So this is the effective mass. So this can be the effective mass of either the electron, which is, this is electron, or it can be the effective mass of the hole. And so this is equals to 1 over Planck constant squared, reduced Planck 1 over reduced Planck constant squared, and the second derivative of E over K. So this is what you are given in your formula sheet, but actually I'm just going to add a bit, because this E is actually a function of kx, or that's a function of k in whatever direction is given, and then you need to take this value at k equals to 0. So kx or whatever k equals 0. So essentially this is they will almost never test this in the exam, but it's still in the formula sheet. So if it is tested, the only way it can be tested is they give you a function of, they give you a E as a function of k, and then you use this, you take the second derivative sub k equal to 0, or whatever k they give you, into this to find the effective mass of electron or hole. So they only give you this, but essentially this can be both m or p, because it depends on whether you are looking at this or this. So this is for conduction band, or this is for valence band. So depending on what function of E they give you, you can find both the electron or hole effective mass using this equation. But it's again, it's rarely tested. So now let's look at direct vs indirect bandgap semiconductor, which is very important. It's very often tested also. So as you can see, this is the this is also another EK diagram, but it's a bit dissimilar because we are looking at different planes of the crystal lattice. Because if you look at the same plane of the crystal lattice, it will just be symmetrical. So to get more information, we look at different planes of the crystal lattice. So to know what these planes are, you can look at the previous video, or part 1, about the crystal structure of semiconductors. But anyways, the direct bandgap semiconductor is where the lowest point of the conduction band, which is here, this is the lowest point of the conduction band, lowest, and then this is the maximum or the highest point of the valence band. So a direct bandgap semiconductor here, as you can see, is where the CB minimum and VB maximum both occur at the same K value. So here K is equal to 0. So they occur at the same K value, while indirect bandgap semiconductor is different, because you can see here's the lowest and here is the highest band of the highest point of the valence band, and so they occur at a different K value, and they require this change, this change here. They require a change in the crystal momentum before the electron can transit. So if the electron were to transit, it will have to transit like this. So it will not only have to undergo an energy change, it will also need to undergo a crystal momentum change. So as you can see, for the direct bandgap semiconductor, however, it can immediately transition without needing a change in crystal momentum. So these transitions are very, very efficient as compared to the transition from indirect bandgap. So actually this transition, this momentum change, can be satisfied through phonon or lattice vibration. This is not relevant now in this chapter, but we'll look at what this means very near the end of this video series about LEDs and photodetectors. So we don't have to understand this now, but just remember that the crystal momentum change can be satisfied through phonon lattice vibrations, and this makes the transition unlikely and not efficient. We'll look at why again in a later video. So for direct bandgap, of course, you don't need any momentum change, so it's extremely efficient. And then this energy is given off as phonon or light. Why this energy is given as phonon or light, we'll look at it in the future, or like the same video on LED and photodetector also, which is near the end. But just remember that the direct bandgap semiconductor will give off the energy as photon, which will make it very suitable for light producing devices. So some applications are like LEDs, laser diode. So all these devices must be made of direct bandgap semiconductor. Whereas indirect bandgap, because of the difficulty of the momentum change through phonons or lattice vibrations, they are more likely to go through defect states. So again, defect states will be explained later. Just remember they are called defect states. So electrons transitions are more likely through defect states, and this makes the energy give out as heat, or heat is just phonon, so it will give out the energy as heat, which makes it not very suitable for light producing devices, and it will make it very inefficient. So actually it can still produce photon, but it's just so inefficient and so unlikely that it is very impractical as compared to the direct bandgap semiconductor, which is a very efficient way. So you can see, you know, LEDs are above 90% now, or even much higher than that today, because they are all direct bandgap semiconductors. So before we end this video, let's give some examples of direct bandgap semiconductor. So some direct bandgap semiconductor is, for example, gallium arsenide or gallium nitride, which is used for making LED. And for indirect bandgap semiconductor, is something like silicon, germanium, and all these, they are indirect bandgap semiconductors. So yeah, that's the end of the part 2 of this video series. And if you enjoyed it, please leave a like and also watch the other videos. Have a great day.